My name is Amit. I'll present the Tensilica IP portfolio for automotive. And this presentation will be co-shared by my coworker Suhas. Thanks for making time to come and listen to this. So we're going to talk about trends. We are going to talk about some of the sensors that are penetrating into the automotive applications. We are going to talk about some of our technologies that are making these, technologies, these kind of applications available on a vehicle. And then we're going to talk about our platforms. So we all know basically about the electrification. That's a new trend that's coming up. The ICE engines or the internal combustion engines at some point of time will be obsolete. So electrification definitely is on the rise. These are like software-defined vehicles. These need a lot more processing than what the traditional vehicles would have needed. And that's where the need for more compute, more processing power comes in. The ADAS to AD, or from driver assist to autonomy, usually needs a change of architecture as well. So today we see a lot of deployments, whether it's partial centralization, zonal, and eventually probably into a centralized architecture. So that process has already started. And the reason we will be able to achieve more performance and more safety is by adding a lot more sensors to a vehicle so that the perception system of the vehicle is bulletproof. There are new applications that are coming into this space. So, for example, monitoring the driver behavior while you're driving for attentiveness, occupancy monitoring, especially targeted for some of the upcoming future applications like robo-taxis. And then the heads-up display, which today is usually on the windshield, but there are further future applications that are being at least considered by a lot of the OEMs. And then on the connectivity and the digital cockpit, there's a lot of data that these sensors are going to generate, and you can almost consider a vehicle as a data center on wheels. The enablement is 5G. Earlier it was 4G. And that leads to a lot of newer applications in infotainment and enabling digital cockpit. The voice and audio connectivity is increasing as an application in vehicles. And then, of course, the in-cabin entertainment. So a lot of the streaming companies are now tying up with the car makers to launch their platforms in this space. So we'll talk a little bit about from sensors, how the perception is enhanced, which leads to a better assist system, and which will eventually lead into autonomy. So if you look at this diagram, we all know that the cars are having a lot more sensors today as they were 5 years back. And the growth chart is that every car, whether it's in L2 category or L1 category, all the way up to L5, as the complexity increases, the number of sensors increases. But today, if you only talk about L1, L2, which controls the majority of the market today, you will have short-range radars, we'll have long-range radars, and we'll have long-range cameras, at least to do applications like forward and real collision avoidance, auto steer to some extent, or adaptive cruise control for most of it. These applications also enhance driver user experience by putting applications like traffic jam assist, highway assist, and so forth. Blind spot monitoring, which used to be ultrasound sensors at one point of time, are either cameras now or radars. So from Tensilica perspective, we have technologies, we have platforms that enable vision, that enable your radar processing, your LiDAR processing, communication, audio, to perform more efficiently into applications that I just spoke about. So let's quickly talk about, we all know that no sensor is perfect. So if you have vision systems, of course, there's a lot more research in vision systems. They are adopted today. It's used for better classification or recognition. But vision systems do fail because of the poor lighting conditions. So to take over those failures, we get radars so that radars are almost weatherproof. You can operate radars in any conditions, and they're potentially long range. But you do come with a lot of noise. So the noise levels are higher in radar, plus from an AI perspective, the classification is limited. LiDAR comes in, it's an excellent source for mapping, but these are expensive sensors. So over a period of time, they will come down. But they are also a little ineffective in rain and fog because they operate on the same principles as vision, which is optical. So we think that the combination of vision, radar, and LiDAR is probably the best solution. Now, there are different implementations on different vehicles. Some don't have LiDARs. Most of them don't have LiDARs today. But eventually, as we see, at least the vision and the radar are most popularly going to be deployed. So from the sensing front-end perspective, there's a perception sensor layer, and that's where we think there are at least 4 cameras, 2 in the front, 1 in the back, 1 in the front, 1 in the back, and 2 on the sides. This could lead to multiple cameras, depending on the chart I just showed you. There are long-range radars, short-range radars, solid-state LiDARs, and ultrasound. So our focus at Tensilica is on the extreme left side and also in the center. So we collect all this data, and then we process it using our technology, which can lead to various performance enhancements from the perception layer and also help on the sensor fusion side. And from our platform perspective, for vision, we have P1, P6, Q7, Q8, and NNA, which is our neural network accelerator. Radar and LiDAR have a different product line. We call it Connex. It's 110, 120, B10, B20. And then we have the Tensilica Hi-Fi and the floating point products, which are used for ultrasound as well as for sensor fusion. So what are the values that we bring to the table today? So I'll start from the extreme right-hand side. So these are soft IP DSP cores. These are SIMD machines with various type of VLIW slots, which offers vectorization both in fixed as well as in floating point operations, which is here. The most important thing also is the extensible architecture. So the customers can tune the architecture and add custom instruction layers based on their specific needs. So we provide a lot of flexibility there. These are definitely more energy efficient because of our architecture coming from Extensa, which is our base platform. And we have the instruction set for efficient processing at lower power. And then on the CPU features on the left-hand side, we can provide efficient control code to manage those CPUs better, and we provide real-time operating systems, or you can use it from the open source community. So I'll quickly take you through some of our product offerings in a little bit more detail. So the first one is a vision platform. Like I said, all of our offerings are based on Extensa architecture. We provide software libraries, as I mentioned, on the left-hand side. But from a product perspective, from down, that is Tensilica Vision P1 DSP, all the way up to Vision Q8, we offer SIMD machines, which are either 128-bit SIMDs all the way up to 1024-bit SIMDs. And we are also, these machines are also capable of running your AI models if you need to, though there are separate products for our AI that my coworker Suhas will talk about. In terms of the radar and the LiDAR platform, which are mostly used for tracking and for classification, Again, these are based on our extensor architectures. We offer the software libraries, which are mentioned on the left. Either these are Eigen libraries, MATLAB toolkits, Nature DSP, or basically a full radar library. But if you look at the offerings from top to the from bottom to the top, we have machines here which are 128 SIMD, which are Connex 110, 256-bit SIMD, which is Connex 120 or B10, and then 512-bit SIMD, which is Connex B20. These chips, these DSPs are also used in communications, and that's a separate segment, but these have a lot of implementation in automotive, especially on the radar application. All of these have common ISAs, and they have what we call the Tensilica instruction extensions, which is the TIE, which is one of our value propositions. We have an audio platform, and this is already there in a lot of vehicles. Again, based on extensor, if you look from bottom to the top, most of the machines here are 64-bit SIMD, except the one on the top, which is 128-bit SIMD. The differentiation here is the VLIW slots. So you look at Hi-Fi 1, which is 2 VLIW slots, and then it goes all the way up to 5 VLIW slots. And that's kind of the performance leader in this space. Hi-Fi 5 is also capable of not just doing a digital signal processing, but also doing AI. So that brings another functionality from this product perspective. Okay. So since we're talking about automotive, we have to talk about ISO 26262 because those are very important for automotive applications. Our DSP cores as well as the toolchain are ISO 26262 certified. We have a lot of customers, tier ones, who are already using our product. And if I talk about these 2 points, the extensor, the base platform, offers the DCLS or the dual core lockstep. So that is important for supporting the ASIL-D certification. And then one of the other products, which is the LX, we call it LX Secure Mode, that supports your hardware isolation for secure boot and the root of trust. So this is kind of high level. We'll be open to taking questions. I'll invite my colleague Suhas to continue and explain the AI side of the platform. Suhas.
Can you hear me? Yeah. Okay, thanks, Amit. I think that was a very good introduction to Tensilica. In general, I think you heard the story that Tensilica's all the DSPs are fundamentally driven by a common architecture, which is called the extensor. And then all these individual verticals that he showed, audio, vision, radar, whatever it is, basically stem from that ISA structure where they can be made flexible and customers can pick and choose what they want to do in terms of what ISA wants to enable. So that's the basic premise. Okay, so everything that we talk about essentially gets sort of upended or shaken around with AI, right? Every place we have AI. So I'll talk about a little bit what do we mean by that. So like Amit just said, you have DSPs, which basically have native good processing based on their vertical, right? So if you want to attach some amount of AI processing, what you would do is fundamentally you would take that base ISA and you would add some machine learning ISA. What would that mean? That would mean basically adding some MAC capability natively to that DSP, ability to actually do vectorization, parallelization of workloads, which is very common to AI. That's the basic premise of how these convolution neural networks run. So basically by adding some custom machine learning ISA, you're able to give lowest area and essentially are able to give the best performance for a very small footprint, and essentially is very attractive when the DSP has sufficient headroom, meaning that the DSP is able to run native applications and run AI whenever needed. So in some sense, it's able to use best of both the worlds. Okay, that's one concept. The other concept is to then ask yourself, if I want more AI capability, what would I do? You would basically take a hardware accelerator block and essentially attach that to the DSP base plus MLISA. And the idea essentially is to offload operations that would run on the DSP into the accelerator. And what do you get by that? Essentially what you get is a huge amount of performance uplift, depending on many conditions, depending on the network profile, and essentially also you get better power. And more importantly, you're getting idle power reduction, which means, let's say I have a workload that was running on the DSP, it was chewing the clock cycles. Now, if I offer it to the accelerator, the DSP can either go completely silent, almost like a shutdown mode, or can actually do other workloads which was more domain specific. So you have the choice of actually uplifting the performance, reducing the number of clock cycles for that particular workload, and also reducing power because you can finish the workload much faster in lesser clock cycles. Then you have the AI Max category, which says, well, I will actually not only take your DSP, your entire platform, but I'll view this from the outside looking in, and essentially what I'll do is I'll invoke these inferences, but I'm looking at this ML engine as a standalone, as a turnkey solution. And that essentially is saying it's very high throughput, extremely bandwidth sensitive, and essentially what you're doing is you're using a host application processor, giving an API, an offload API, and essentially saying, now you can offload, my host processor can do whatever it has to do, my ML engine can work independently, and both can coexist. So the story becomes base being add MLISA on the base DSP, boosted by adding some hardware accelerators, and then make it turnkey solution in the end. Okay, so that being said, I think Amit already touched upon the different use cases. Okay, so like I said, everything is being upended with AI, right? So you had all this along, you had driver cabin monitoring, DMS, OMS applications that were using CV-based workloads. Slowly and slowly, we see all the time is people asking us to move from some CV application into an AI workload. It's happening all the time. What does that mean? Like Amit said, there's vision, radar, comm, audio. Some of these applications, people are coming and saying, well, we would like to attach some AI on it. I would like to do some AI on it. It could be AI-based, could be Boost, could be Max, whatever be the case. Now, typically in these kind of applications, the AI base is a good category where it's multi-sensor, very low power, lowest area, some AI capability, but still a lot of domain-specific computing. Then you have this around tens of tops like ADAS, level 2, level 1, level 2 plus kind of thing, where you have this AI engine, like I talked about, in an AI boost category, where you would take the domain-specific compute and essentially throw workloads onto the AI engine. And last but not the least is more as the level 3 plus autonomy, hundreds of tops, where you would have these different subsystems connected through some kind of NOC, a network on chip, and all these things essentially will give you the ability to do both AI, both different kind of domain-specific compute and AI. So all in all, what it means is that you have AI that is required at the lowest tops, tens of tops, and hundreds of tops. So that's the basic premise of this argument. So if you step back, if you were coming to Tensilica or an IP vendor and you were an SoC maker, what exactly are you trying to find out? You obviously want to target not just only one market segment, but you want to build a profile that basically you can run on multiple, you can make multiple SoCs from it depending on the market segment you want. High-end, mid-end, low-end, whatever you want. So if you step back from an IP perspective, what you want is essentially a hardware IP that basically you can take as a soft IP, right? You want a software tool chain that can take these compilers, those different workloads, and run very efficiently. You want some design flexibility, meaning that you want to make sure that you are not designing only for what is out today. AI workloads continuously change. This is a very fast-moving space, and you have the ability to be flexible, and your design should be able to allow for flexibility. Scalability is important. Like I said, you have low tops to tens of tops to hundreds of tops, and given the fact that you will be targeting your SoC for multiple market segments, you want to make sure you are getting scalability in one single profile. You don't have to go to 5 different IP vendors to build scalability. And last but not the least, which is I think the least spoken term, I think, is pre-silicon verification. So you don't want to wait for you to go out and do an FPGA evaluation and go off and do different things before you finally say this IP is good for me. You really want a pre-silicon verification environment. Okay, that's exactly what Tensilica does. It's been doing this for almost 20 plus years. And this is essentially the claim to the fame, right? So essentially is that you have an RTL soft IP. You come to us, we give you a soft IP. It's not targeted to a certain process node. You can take it for different process nodes. We give you AI compiler and software stack. So it could be a CV workload, an audio workload, an AI workload. It all works homogeneously in one single environment, in a single IDE, in a single compiler toolchain. Simulation, like I said, is important before you tape out. You want to have some system C environment where you can take these workloads and run them and see performance. Now, I would like to be very proud to say the system C simulator we have is very, not only sometimes, I like to say, instruction set accurate, but also instruction set very complete. So it's very accurate, and you can profile these things very, very efficiently, and you know how many cycle count you have. And that way you know when you go to the last step, which is the RTL, test bench, or FPGA, whatever you want to do, SOC, want to preview it, you want to make sure that you basically have faith in your system C simulator. And this is built on years of expertise in Tensilica. And I put this loop here because this is what I call as hardware-software co-design. You want to be in an environment where the hardware, software, toolchain, design are all moving in one single flow. You don't want to go and have to tweak different things from different IP vendors. So that being said, just one slide here for software compiler. Why I stress on it? Because this is an AI talk for automotive. And if you're an SoC provider, I think the way to look at this thing is to say, listen, I don't want to go program the accelerator and the DSP individually. I want to go and do what I do best, which is to work on use cases, which to work as end user use cases where you can design networks in different AI work frameworks, TensorFlow, MXNet, PyTorch, you name it, okay? But you want one front end that can actually ingest your network and run the entire graph. AI folks call it graph or what you want, like it's a compute acyclic graph. That's basically what it is. And the idea is that you throw this on the compiler toolchain. This is our compiler toolchain, and let the graph be optimized by us. You don't have to optimize it. You don't have to know how to quantize things. And then, depending on what platform you choose, it should be able to actually target that code. So what in the end you will get is a very simple API for that particular platform that then you can go and deploy. So as an end user, the point is simple. You work on the system problem, on defining the network, on what network is best for use cases, and you come on the right-hand side to say, once I get those APIs, I'll then deploy them the way I want to deploy, and let everything Tensilica worry about the middle. So the idea is scalable, high-performance, end-to-end compiler, time to market essential. You want to make sure you get there fast and don't get bogged down by programming the actual DSPs and the accelerators themselves. Okay, so all that being said, Tensilica vision, customer success is the following. There are a couple of partners that we mentioned here, people who have taped out and they have talked about publicly. There are many more in the pipeline. Obviously, not everything we can declare here, but the point is you can see, for example, a GeoSemi or a Black Sesame or Neuron or Toshiba or SemiDrive or a VIR. They've all used these DSPs, radar or vision, like Amit said, and used them for domain-specific computing. Okay, so that's a long-standing success. And again, I have to say, this is only a small sample of automotive customers. There are lots of customers on vision that use things on vision all the way from camera, digital still camera, to smartphones, to IP cameras, whole kinds of slew of things. Okay, I'm just giving you a sample here. Similarly, on radar, you have Marvel, you have Andes, NXP. By the way, I would strongly encourage you to come to the Cadence booth. Many of these things that we're talking about in these terms of platforms here, we actually are showing them on our booth. You can see the physical product, the physical board yourself, and in some cases actually see live demos running on our platforms here. So strongly encourage you to come over and see the demos for yourself. So yeah, bunch of partners here. Like I said, many other things exist. This is just a very small subsample. In the end, like Amit said, we'd like to end thanking everybody, but a very high-level summary is, we are a leading supplier of IP for edge computing. I don't know how many people know, but on a yearly basis, Tensilica sells or prioritizes more than 7 billion IPs in a year. And over the last 7 years, 6-7 years, there's more than 42, 43 billion IPs already produced. And that's huge. It's not millions, it's billion, to be honest. So it's a staggering number. And our tools have been used across many different applications. Obviously FUSA, like Amit mentioned, is a big one. We have ISO 262 compliant processors, and our Tensilica DSPs and AI solutions are used for automotive grade and also non-automotive applications. And we have a very rich environment of third-party providers and partners. Come to our booth, talk to us. Happy to talk to you, and Amit and I will be here to take one of your questions. Thank you.